Today is September 15th. We're going to move on with our notes to start the class off with. So we're going to start with the page that says active and passive margins. So there's two types of margins on the side of a continent. So you have an active margin and a passive margin. So if you picture like the continent of South America, the side where the west side is an active margin. So it's a zone of intense geological activity, and it is where the oceanic plate is hitting the continental plate. So it's where that oceanic plate is sliding beneath the continental plate. And as the oceanic plate slides beneath the continental plate, remember that hot magma, as it heats up, the density is less and less. It's going to rise up and create mountains along the shoreline. So we've got our oceanic plate going under, we've got our mountainous shoreline. So you can imagine as it's breaking down chunks of the earth, it's creating a turbulent area, it's creating earthquakes. So it's going to have a steep rocky shoreline, a narrow continental shelf, and a steep continental slope. A passive margin is the edge of a continent where there isn't two plates meeting. So this would be the other side of South America. There isn't another plate meeting it. It's a continent and it slowly slopes into the ocean. So it's just where the water meets the land or where the current water level is. If the water level was to change in 50, 100 years, if global warming keeps going and the water level changes, this margin level would change. So it's not a plate boundary. It's inactive, meaning you're not going to have earthquakes there. It's got flat coastal plains, it's got wide continental shelves, and it's got very mild gradual continental slopes. So if you look at this picture, you can see a little bit better what I was talking about. So here's where our Andes Mountain are. So here is our volcanic island. This would be our waterline or our beach area. We've got our continental shelf is extremely shallow. We've got a massive continental slope. We really don't have a continental rise at all because it's falling directly into the ocean. That's where our trench is. That's where that plate is sliding under. Over here, there is no plate. So we have a very wide, flat continental shelf. We've got a continental slope and a continental rise that are pretty mild. Besides your continental margin, the other area of the ocean or the other basin that we're going to touch on is the deep ocean basin. And in the deep ocean basin is where most of the sea floor lies. It's around 3,000 to 5,000 meters. It's almost flat. We call it the abyssal plain, like you're going down into the abyss or you're going down into the ocean. It's dotted with submarine volcanoes called seamounts. So volcanoes can come from when one plate slides beneath the other, but volcanoes can also come from when there's a weak spot in a continental plate. When there's a weak spot in a continental plate, that magma or lava rises up and creates an area of land. That area of land might not extend all the way to the surface of the ocean and create an island, in which case we say it creates a seamount. It's a mountain under the sea. There can be a flat top seamount called a guyot, and there can also be a trench. So in this abyssal plain, it's going to be dotted with these volcanoes and seamounts and guyots, and then it's going to have a trench. That trench, the deepest one, is the Mariana Trench. It's 36,163 feet. We're going to talk more about it in just a second. Here is a movie for you to watch on seamounts. I suggest you watch it. It will explain how they work and why most of this abyssal plain has nothing on it. It's like being in the deep abyss. Light can't reach that low. But when you're at a seamount, we've made a mountain. We've raised this up to the surface. So we can get photosynthesis going on here. And if we can get photosynthesis, we can have producers. And if we can have producers, we can build an entire food chain. So these seamounts are areas of a lot of biological diversity and an abyss area where you typically wouldn't see any. Here we have our guyots. So guyots are flat top seamounts. We have an atoll. We're going to talk a little bit more about those in another chapter. And then we have an active volcano. This active volcano could also be an island. So a seamount is any submarine mountain of volcanic or tectonic origin. The Mariana Trench. The deepest point of the Mariana Trench is called the Challenger Deep. It's so named because the vessel HMS Challenger, it's located 210 miles southwest of Guam off the Mariana Islands. It's 13,740 feet deep. Challenger Deep is the deepest point in the Mariana Trench. It is actually deeper than that average 13,000 feet deep. If Mount Everest, which is the tallest point on Earth, were to be set in the Mariana Trench, there would still be 2,000 meters or 7,000 feet of water before the top of Mount Everest were to touch the bottom of the Mariana Trench. The pressure at the deepest part of the Mariana Trench is over 8 tons per square inch, and there have only been 3 people to ever make it to the bottom of the Mariana Trench. If you look at this map here, you can see here is the coast of Eurasia. We've got the Mariana Islands, and if you zoom in, right off the Mariana Islands, we have the Mariana Trench. The ocean floor at Sept depth, so at the bottom of the Mariana Trench, the ocean floor is made of a pelagic sediment known as biogenous ooze. It's composed of shells, animal skeletons, decaying microorganisms, plants. It's very viscous, meaning it flows very easily. It's not as thick as typical sand or typical ocean floor you would find. They have crabs and anglerfish. There's over 200 different microorganisms at the bottom of Challenger Deep, which is the bottom of the Mariana Trench. There are some specially adapted fish that live there. We're going to get a little bit more into that when we start talking about ecosystems. So here are examples of those mountains or those seamounts where they would be in the ocean. So in the same way that plumes rise buoyantly in a lava lamp, plumes of hot mantle rock rise buoyantly within the mantle. We already said that they form when the ocean crust goes beneath the continental crust. We get those mountains formed by that same process. When a plume rises to the shallow mantle, it partially melts, and the melt upwells to the surface, erupting as a hotspot volcano. Hotspot volcanism is unique because it does not occur at the boundaries of the Earth's tectonic plates, where other volcanism occurs. So these areas that are highlighted here are areas of volcanoes or lines of volcanoes. You can see the bright red is where the hotspot is. You can see as the plate moves and as it goes through subduction, it keeps creating new hotspots. So this area, this volcanic hotspot, is where that super hot magma is rising, and every time it rises there, it creates a new island in the crust, creates a new volcano in the crust. It might not reach the level of, if it reaches the level of the ocean and above the ocean, it becomes an island. If it doesn't, it becomes a seamount. And every time that plate goes through subduction, it moves that island a little bit, and then this hotspot starts creating a new island or a new seamount. And you can see how they track upwards through this Pacific Ocean basin. Right at the center of the mid-ocean ridge, the plates are pulling apart, and this leaves a depression in between the two plates known as the Central Rift Valley. The floor and the sides are riddled with crevices and fractures, and seawater seeps down through those cracks, and as it gets heated to high temperatures by the mantle, it's forced back up through the crust and emerges as a hydrothermal vent or hot spring. If you've ever been to Hot Springs, Arkansas, these hydrothermal vents are working in the same way. So the water is seeping in through the Earth's crust at the bottom of the ocean. It's getting superheated. As it gets superheated, it's less dense and it rises back to the surface and it emerges, creating this hot spring. Hot springs can range from 70 degrees Fahrenheit to 660 degrees Fahrenheit. And it appears that a hot spring is smoking when a hot spring or when a hydrothermal vent goes off. It looks like they're smoking at the bottom of the ocean. That's not actually smoke. It's water. Water is what's coming out of those hydrothermal vents. What you're seeing is a buildup of minerals it's picked up while traveling through the Earth's crust. And there is a video right here for you to click on to watch a short little clip about hydrothermal vents. And that is it for the end of these notes. When you are done with your notes, you have 2 assignments for today. The first one I think is kind of fun. Sorry, I'm not on September 15th. The first one is kind of fun. You're going to click on ocean floor on Google Earth questions.